All right, the next thing we're going to talk about here is Newton's first law. And Newton's first law is actually relatively straightforward. What it basically says is if you have an object that's at rest and you don't poke it, it will stay at rest. Now, in the simplest instance, this has to deal with an object that is stationary. So if you take a look at your screen, with you being the observer, and you look at this black box in the center of your screen, right now this black box is at rest. If this were an object or an animal or something floating out in space, it doesn't really matter. If you didn't touch anything, it would probably still stay there. Now, at rest can actually be extended a little bit. Not only can our object stay stationary, but at rest actually also allows for our object to move at a constant velocity. If you want to think about it this way, if you have an object like this floating out in space and you push it, it'll go forward, and there's actually nothing to stop its motion from continuing forward. And if you've ever watched any sci-fi movies when the person falls out of the space station or whatever, they float off into the distance forever. That's because, typically speaking, they're at rest and no external forces can come in and mess with them, which is kind of why they float off, you know, into the distance. It's kind of terrifying to think about, but it is what it is. Now, there's a very distinct reason why both it being stationary and moving at a constant velocity is required, and that's due to the fact that physics should be independent of who's observing it. So right now, instead of you being the observer, I have this little stick figure in the bottom observing it. So right now, the stick figure in the bottom and you are both going to agree that this object has a velocity of 0, this black box, because you're not moving. The reason why this constant velocity has to be included in our definition at rest is what happens if I move the observer. So what you're basically seeing here is the observer is moving according to you and the box is stationary. However, if we were to be the observer, what we would actually see is we'd see this box move left. So if you take a look at this final spot at which this observer is at, they've seen the box move. So what they basically see is the box starts off in the middle and has moved to the left. In other words, because they are not capable of seeing their own motion, what they've actually seen is the box starting off like this and the box moving to the left, which is different than what you see. The reason for that is it's not possible for you to see your own frame of reference. And the reason why we incorporate this into our study of physics is the question becomes, if both you and my hypothetical stick figure observer here are seeing different things, who's right? And the overall answer is it doesn't matter. Even though you might not make the same observation, both of you will agree on the same laws of physics. Both of you can see an object move at a constant velocity if nothing acts on it. And this independence of observer makes physics both the most egalitarian of all science fields, because your opinion and your perception doesn't matter, and it's also the most accepting, because you must accept every measurement made by an observer in every reference frame. Now, the complicated thing about that, and what we're going to talk about next, is how do I reconcile the laws of physics between these two observers? And basically, we reconcile them by using something known as a coordinate transform. The coordinate transforms we're going to deal with are Newtonian. They only work at very low velocities. But there's a lot of cool stuff, like if you're interested in things like astronomy and special relativity, that actually start getting drastically different observations being made in systems in which our observers move at high velocity. But we're going to keep it simple for now.